that is given by, I need my cheat sheet, Alexander Korotkevich.
That's correct.
And it's about discovering new salts, salt hydrates.
Okay, thank you. Everyone can hear me, right? Nice. It's a pleasure to be here. I want to thank organizers for giving this opportunity and for the beautiful workshop. And I wanted to entertain you with a small demonstration right away because it's the last talk before the lunch and everyone is with their thoughts somewhere else probably. So I have a couple of hand warmers in my hands and that I'm going to activate them right now. And if you could pass it around, you will hopefully feel that they're getting quite hot. Oh, it's from that point. I'll also run it in parallel on a video so that you can better see what's happening. So I have some liquid inside of this container and a metal disc. And when I'm flexing on the disc, I'm activating some process that makes the content of what is inside completely opaque. And what is actually happening is that by flexing this metal disc, I trigger a crystallization process of this super saturated solution of sodium acetate. And I obtain this product, sodium acetate 3 hydrate, and some heat is released, which you fully can feel. So this sodium acetate is an ionic compound, it's a salt, and what is interesting is that this process is reversible, and if I drop my crystallized material into boiling water for some time, I will dissolve my salt in this water by using the external heat, and after all, this material will become liquid again. So the purpose of this demonstration is to show that there are these materials called salts, and they can form hydrates by absorbing water from the gas phase. And this process is accompanied by release or absorption of heat. And it's also reversible. So dependent on the direction, the heat will be either released or absorbed. So a slightly more ambitious goal than my demonstration is to use these materials for domestic heat storage. So you can imagine that you have a reservoir with this material, like TCM, thermochemical material, and in colder time, which can be winter or night time, we will hydrate our crystals and release heat that will heat up the building. And in warmer time, which can be summer or day, we will recover the material by applying some external heat. So why this is important is evident from that donut plot, which shows the proportion of energy consumed in different sectors in for domestic use. And if you look at that, you will see that most of the energy consumed in buildings is actually for thermal end use. So the materials that we are studying are quite promising in that area, but still require some improvements in certain directions. So I'm going to focus on the direction of energy density. And if we look at what we have, what we know, we will see that the chemical space is significantly larger than the available data. So the discovery of new materials will be very likely, will be very helpful. So we were wondering if we can apply AI or ML tools to facilitate the discovery of these materials. And we started from building a predictive model. So I'm going to briefly walk you through. So we have our reaction written in chemical notation. So we will need to obtain some sort of representation of this reaction, which will be used as an argument for a predictive model. And this model will be trained using existing thermochemical data. And hopefully, when the model is obtained, we can apply it to some materials for which the properties are unknown. So regarding the data that we have, so that's approximately what it looks like. We work with tabular data. If we look at that, we'll find out that the input information is encoded in these 3 columns. So it contains the composition or the stoichiometry of the salt, the numbers of water molecules in the initial and final material, and all the rest of the columns, they contain properties that we can predict in some way. So we managed to scrape that amount of data. Most of it comes from the DFT simulations and another significant chunk from the miscellaneous experiments. It's not much, but that's what we have to work with. The properties that we predict, as I mentioned before, are related to energy density. So the first is hydration enthalpy, that shows how much energy is released per water molecule absorbed in a crystal structure. Next is just the gravimetric density, and by combining the two, we obtain the volumetric energy density of this material, so how much energy is stored per cubic meter of material. So next I'm going to talk about how we obtain representations and what kind of architectures we use. So again, if we look at our data, we will see that the composition of salt and the reaction stoichiometry is already available for us. So this is good, this can be used. But after some search, we realized that the structural data, so more information on that materials, is actually quite hard to get. So because of that, we will rely on this very simple reaction stoichiometry based representations and work with that. So regarding the architectures, we use a few. So the first is based on standard magpie featurization. So we extract the composition of the salt, pass it through the featurizer, and this way obtain a composition vector. We also extract the loadings, M and N, and by appending them to the composition vector, we obtain the reaction representation. And then the only learnable block here is the deep network that will predict the property. Next architecture is inspired by the LMNet architecture, published some year before. So here we obtain, first, we extract the individual elements and their amounts. The amounts are converted into fractional weights, and each element gets an encoding. And after that, we pool them together in a composition representation, again, appending the loading and do the same as before, training a feed-forward network. And the next representation, the next architecture is based on the roast architecture. So I wanted to make a step back and explain a little bit how it works for predictions of properties of compositions. So again, we extract individual elements representations and atomic fractions. And then this information is used in several learnable blocks. The first is multi-head attention. So essentially, we treat each element as a node of a dense graph, and we perform message passing operations between these nodes. This way we obtain so-called context-aware element representation. Next is the learnable pooling layer, and after all, the predictive model. So I want to acknowledge the authors of this paper, and personally Rhys Goodall, who is present here, for publishing the code. This is a great contribution to open science. We could use and adapt this, so thank you for that. But coming back to our problem, our situation is slightly different. So we also have this loadings information. So we developed two modifications of this architecture. In the first, we append the loadings to the elements representations before the learnable blocks, which are used to transform the initial representations. And then we call it React Rost E. E stands for the elements. And the next is going to be React Rost C, where we append the loadings after the learnable representation transformation. So just to summarize what I've just told you, we use two architectures based on the predefined representation, also based on stoichiometry, and we use two architectures based on learnable representations. So next I'm going to share some results of how these models work. So first we performed the 10-fold cross-validation on existing data. So this is the prediction versus target for the volumetric energy density values for unseen data. So we get quite an impressive result, I would say, with this very large R square. So this is the quantification of errors for each of the models. So what we can see is that architectures based on learnable representations outperform architectures based on predefined representations, and architectures based on presence of elements outperform architectures based on the physical properties, which is surprising, but that's what it is. Another interesting reference here is this dashed line. So we happen to have some duplicates in our data that were present both in DFT and in experiments, and the dashed line shows the average difference, the average deviation of these points. So what we can see is that all the architectures that we apply are more accurate than this difference between DFT and experiments. So we also did that for two other properties that I mentioned before, the density and the hydration enthalpy. We get qualitatively similar results, except the R square for hydration enthalpy. This is significantly lower. But if we look at the errors, they are actually not so bad. We are still below the difference between DFT and experiments. So at that point, we thought, okay, our model works. So can we do the next step? And the next step would try to predict some new reaction properties. So to do that, we needed to find some materials that are not present in our training set, which is on its own quite scarce, and also that exist and that are stable. So without going into details, we performed a literature search and we found a list of 29 salts that are proven to exist, but that have not been studied yet in by some thermochemical method. We don't need to look into all the details of this chart, but we also further classified these hydrates into those for which the synthesis was either known or unknown, and also the dehydration mechanism. So we picked these two salts just because for our experimental collaborators, it was easy to make them. And we performed differential scanning calorimetry measurements and also run some predictions for them. So let's see the result that we have obtained. So the dashed line here represents the value obtained in experiments, and the points correspond to different architectures. So for both measurements, we can see that the architectures with predefined representations somehow underestimate the value, while the architectures with learnable representations for some reason overestimate the value. Interestingly, is if we ensemble these predictions, we get very close to the experimental value. So this is a subject of exploration, how to better do that, but this is the result that we have so far. We also ran some predictions for salts for which the dehydration mechanism is not known. So that would be something that we would suggest to experimentalists to study. And we compare these predictions to some reference reactions that are considered very promising in the community. And what we can see is that for several of them, we notably outperform those reference reactions in terms of volumetric energy density. So this is quite cool. With that, I would like to conclude. I'm not going to read the conclusions, but I would like to focus on one possible outlook. So I showed you, hopefully convinced you, how these approaches work for predictions of hydration of salt reactions. But what if we look at it more generally, if we consider a reaction of some substrate binding some kind of ligand associated and an effect associated with this reaction, can we generalize it to any of these reactions? So we are open to suggestions in that direction. I want to thank my collaborators. Please talk to me if you want to discuss this research more, or to my supervisor, Alberto Perez de Albertis, who is also present at the workshop. I want to thank you for your attention and ready to take questions.
Thank you very much, also for staying perfectly in time. Questions. So Emma first.
Thank you. That was a really wonderful talk. I have two very, very quick questions. The first was, did you ever look at going from, because I think on all of your examples, you looked at anhydrous, so not hydrated, going to hydrate. Did you ever look at the example of, say, a monohydrate going to a dihydrate? So already hydrated species going to a more hydrated species.
In our data, we have different examples, and it's generally M to N, so M is not necessarily zero.
Okay.
M is often not zero, but what often happens is that in nature, these reactions occur from dry salt in one step to like 6 times hydrated, for example.
Okay. And then my second question, more of a comment, because you were thinking of, what could you possibly do, molecule with some other thing. Would you be interested in looking, well, I suppose this is more of a comment, but solvation, so not hydrate being the solvent, but any sort of bulk solvent, it's probably the most important interaction in any sort of chemical or biological reaction is how does that molecule interact with the bulk solvent around it? So something to think about, not necessarily a question. Thank you.
Yeah, thank you. I think it's a good suggestion. Actually, we were thinking about something along these lines. In principle, what you need is to have a substrate that can be that can have like a defined stoichiometry, which we can extract, and a certain like ligand that or like solvent that binds to this. Whatever it is, if you have like a database where you have a lot of substrates to which one single ligand or like a few ligands are binding, that would work, I think. Thanks.
Hi. I had a quick question about your data set. So it's really hard to assemble them, and you downloaded them from a few sources. And then you start to have problems with some internal consistency because they were measured in different ways, and you have partly experimental and partly computational ones, data. So did you include like this potential variation in the data on account of different sources into your models as some kind of noise?
That's a good point. Unfortunately, we do not yet explicitly include that. So at the same time, yeah, there are ways to do that because in all the publications that we use to extract data, there is also information on what kind of errors they expect. Also, the ROST architecture, it allows to use so-called robust loss that models each point as a we predict not a mean value, but like a distribution. Yeah. So that can be combined together, I think.
Okay, thank you.
Yeah, thank you for the talk. If I understood correctly, your model does not account for the crystal structure, right, itself. So maybe then my question is, have you seen in your data any compounds that would have two phases, and you would know like experimentally or from like maybe experimentally what would be the variability? Like, so I'm just trying to rationalize. It looks like your model works very well and prediction is kind of very robust, but it does not take into account crystal structure. I'm trying to understand whether what is the kind of basis for that in terms of experimental data already. Maybe there is not much such variability at all.
Well, in that sense, yeah, that's a completely fair point. All those methods, they are agnostic to polymorphism in crystal structure. So you predict for one stoichiometry, there can be several polymorphs, so that's not taken into account. However, at least for the DFT data, which is the majority of the data, the crystal structures have been obtained, and they were all stabilized for the lowest energy polymorph, for the point that is like on the convex hull, for example. The problem is that they are not published, so that's why we cannot use them. But yeah, I guess partially it addresses what you asked.
Yeah, great talk and work. I want to go back to the point that Milica made earlier about different sources of data. There are methods available to very effectively keep track of different sources of data. You can look up multitask learning or multi-fidelity learning. Great ways to bring different sources of data together, experimental and computational, keeping track of where it's coming from. And it works well, especially if there is good correlation between the different sources, and I assume there will be between your DFT and experimental. And also how you split the data during your model building, right? How you do your cross-validation, splitting, things like that can be, there are solid, clear-cut approaches to do this, because your data set is dominated by DFT results.
Correct.
But you're comparing, ultimately the model is mandated to make predictions that get compared to experimental results, right? So there are ways to handle this quite effectively. So perhaps this comment is helpful.
Thank you. It is.
Okay, I see no further questions. So let's thank our speaker again. And now we're